Hey, you ever been in a totally dark room, fumbling around, unable to see a thing? Then bam! Someone flips a light switch and suddenly everything around you is crystal clear.
It's almost like magic, right?
Yeah, that feeling of going from total blindness to seeing the world, that's what we're digging into today. What is this magic that lets us see?
It's all thanks to light, and today we're going to explore two of its most fundamental behaviors. Reflection, you know how light bounces off things, and refraction, how light bends when it goes through different stuff.
Reflection and refraction.
Yeah.
Okay, they might sound a bit technical, but honestly, you see them in action every single day.
Oh, absolutely.
Think about your reflection in the bathroom mirror, the way a straw in a glass of water looks bent, or even why a rainbow pops up after it rains.
Yeah. All these cool things happen because of how light interacts with surfaces and different materials.
That's right. And our understanding of light has really grown over time, hasn't it?
It really has. We
Yeah.
started out thinking it just traveled in straight lines, like tiny little rays shooting out from a light source. And for a lot of what we see every day, that's actually a really helpful way to think about it.
Okay, so light is straight rays, like sunshine coming through a window.
Exactly. The fact that if you hold up your hand in sunlight, you get a pretty sharp shadow.
Hmm?
That supports the idea of light traveling in straight lines.
Makes sense.
However, when light bumps into really tiny things, it can actually bend around them. That's called diffraction. This bending behavior tells us that light also has properties of waves.
Wait a minute, diffraction. So light is both straight rays and waves. Like it has a double nature.
It does. It's one of the really fascinating things about light. Sometimes it acts like a wave, and other times it behaves as if it's made up of tiny particles. It took scientists a while to figure this out.
I bet.
But for what we're focusing on today, reflection and refraction in everyday scenarios and with mirrors and lenses thinking of light as straight rays is going to be super useful.
Okay, so we're keeping it simple with the straight ray model for now. So what exactly are we trying to understand about these light rays today? What's our mission?
Our goal is to really grasp how light reflects or bounces off surfaces and how it refracts or bends when it moves from one transparent material to another, all using the straight line idea of light rays.
Okay.
And we're going to see how these principles are used in things like spherical mirrors, which are curved mirrors.
Spherical mirrors like those funhouse mirrors that make you look super tall or wide.
Exactly. But also the mirrors used in car headlights to spread the light out, or, in telescopes to gather light from distant stars. So let's dive into reflection first.
Right.
Picture looking at a really smooth, shiny surface, like a mirror. What happens to the light that hits it?
It bounces right back at me so I can see my reflection.
Precisely. And this bouncing back isn't random. It follows very specific rules called the laws of reflection. The first law is that the angle at which the light ray hits the mirror, we call that the angle of incidence,
Angle of incidence. Okay.
is exactly equal to the angle at which it bounces back, the angle of reflection. Imagine throwing a tennis ball straight at a wall. The angle it goes in at is the same angle it comes out at.
Equal angles in and out. Got it. What's the second rule?
The second law tells us that the incoming light ray, the incident ray, an imaginary line that's perpendicular to the mirror's surface where the light hits, we call that the normal
The
line.
normal, perpendicular up
And
down.
an outgoing light ray, the reflected ray, all lie on the same flat plane. Think of it like drawing these three lines on a piece of paper. They'll all be flat on that surface.
So these rules apply to any reflecting surface, even those curved funhouse mirrors.
Absolutely. Every time. Now, you're already familiar with what happens when you look in a regular flat mirror, what we call a plane mirror. What are the key things you notice about your reflection?
Well, it looks like me standing up, not upside down, so it's erect.
Mm-hmm.
It also seems like it's behind the mirror, and if I step forward, my reflection steps forward too. So same distance. And it's the same size as me, right? Oh, if I wave with my right hand, my reflection seems to wave with its... That's
Exactly. The curved surface of that spoon acts like a curved mirror, and the most common type of curved mirror is a spherical mirror. Imagine taking a slice out of a shiny ball. That curved piece can be a spherical mirror.
okay, a slice of a sphere.
Now, there are two main types, concave and convex.
Concave and convex. How can I easily remember which is which?
Think of a cave, it curves inwards. A concave mirror is curved inwards like the inside of that spoon, like a cave.
Okay, cave-in concave.
Right. A convex mirror is the opposite. It curves outwards, like the outside of the spoon. It bulges out. Your textbook probably has a figure showing this. The back of the mirror is usually shaded to show it's not the reflecting side.
Okay, concave is curved and like a cave. Convex bulges out.
Right.
Got it. So these curved mirrors have their own special terms, right? Like the pole and the center of curvature.
Yes. The pole P is simply the center point of the reflecting surface of the spherical mirror. It's like the very middle of the shiny part.
P for pole, the center point.
Now, imagine that spherical mirror as being part of a complete round ball. The center of that imaginary ball is called the center of curvature, C.
C for center.
It's really important to remember that the center of curvature is not part of the mirror itself. It's just a point in space. For a concave mirror, it's in front of the reflecting surface, while for a convex mirror, it's behind it.
Okay, the pole is on the mirror. The center of curvature is the center of the imaginary ball. What about the radius of curvature?
The radius of curvature, or is just the radius of that imaginary sphere. So it's the distance from the center of curvature, C, to any point on the spherical mirror surface, including the pole. Simple enough, right?
Yeah, R is the radius. Makes sense.
Now, if you draw a straight line that goes through the pole in the center of curvature, C, that's called the principal axis. Think of it as the main line of symmetry for the mirror.
Principal axis, the central line through P and C.
Got it.
Now, what's the principal focus? That sounds important.
The principal focus, F, is a really important point. It's where activity 9.2, the one where you can burn paper using sunlight and a concave mirror, comes in.
Oh, yeah.
But a big warning here, never look directly at the sun or its reflection in a mirror. It can seriously damage your eyes.
Definitely don't want to do that. But I remember hearing about focusing sunlight to start fires. That's it.
Exactly. When you hold a concave mirror in a way that it reflects sunlight, which comes in as essentially parallel rays because the sun is so far away.
Right, parallel rays.
Those reflected rays all come together, they converge at a single point. That point is the image of the sun, and it's what we call the principal focus, F of the concave mirror.
So F is the focus point.
Yes, and the concentrated sunlight at the focus creates a lot of heat, enough to burn the paper. Now, if you have a diagram like figure 9.2a of a concave mirror with parallel rays hitting it, you'll see they all converge at the principal focus, F. For a convex mirror, if parallel rays hit it, they reflect outwards and appear to be coming from a point behind the mirror. That point is its principal focus, F, see figure 9.2b.
So concave mirrors bring parallel light rays together at F, and convex mirrors make them look like they're spreading out from F behind the mirror. And the focal length.
The focal length is simply the distance between the pole, P of the mirror, and its principal focus, F. So F is just the length P to F.
P to F is F, easy.
Now, spherical mirrors have a circular edge, right? The diameter of that reflecting circle is called the aperture. Usually when we talk about image formation, we focus on mirrors where the aperture isn't too big compared to the radius of curvature. For these smaller aperture mirrors, there's a really useful relationship.
Oh, yeah? What's
Between the radius of curvature, R, and the focal length, F. The radius of curvature is twice the focal length, or R equals 2F. R equals 2F, so F is exactly halfway between P and C.
Precisely. It means the principal focus F is located exactly halfway between the pole and the center of curvature C. Okay, R equals 2F. That's a good one to remember. So now we know the different parts of these curved mirrors. How do they actually create images? We know what happens with flat mirrors, but what about these spherical ones?
That's the next big question. Let's think about how these curved mirrors form images. Activity 9.3 in your materials, where you look at a candle in a concave mirror from different distances, is super helpful here.
The candle experiment.
If you do that experiment, you'll see that the image of the candle changes a lot depending on where you place it relative to the mirror.
So the image isn't always the same size or in the same place. It changes.
Exactly. The characteristics of the image, whether it looks real or virtual.
Real or virtual? What's the difference again?
A real image is one where the light rays actually converge and meet. You could project it onto a screen, like a movie projector. A virtual image is where the rays only appear to come from a point, like your reflection in a flat mirror. You can see it, but you can't project it.
Okay, real can be projected, virtual can't. Got it.
So whether the image is real or virtual, whether it's upright or upside down, erect or inverted, and whether it's bigger, smaller, or the same size as the actual candle, all depend on where the candle, the object, is positioned relative to the mirror's pole. P, principal focus F, and center of curvature C. There's a table in your resources, table 9.1, that summarizes all these different possibilities for a concave mirror. It's worth looking at.
Let's go through a few from that table. What if the object, like a star, is super far away at infinity?
If the object is at infinity, like those parallel rays from a distant star, the image forms right at the principal focus, F. It's going to be very tiny, almost a point, highly diminished, and it will be a real image. You could project it and invert it upside down.
Okay, infinity goes to F, real, inverted, tiny. What if I bring the object closer so it's beyond the center of curvature, C?
Then the image will form between the principal focus F and the center of curvature, C. It will be smaller than the object, diminished, real, and still inverted.
Beyond C, between F and C. Still real, inverted, but just diminished now. And if I place the object exactly at the center of curvature, C.
In that special case, the image also forms at the center of curvature. It will be the same size as the object, but it will still be a real and inverted image.
At C. At C. Same size, real, inverted. Interesting. Getting closer. What if the object is between the center of curvature, C, and the principal focus, F?
Now, the image forms beyond the center of curvature, see, so it moves further out and it becomes larger than the object, enlarged. Still real and inverted, though.
Between C and F, beyond C,
Right.
large, real, inverted. And what happens if I put the object right at the principal focus, F?
If you place the object exactly at the principal focus, the reflected rays become parallel after bouncing off the mirror. They don't converge. In this ideal case, the image is said to form at infinity, and it would be highly enlarged, real, and inverted.
At F, image at infinity. Okay, so in all those cases, the image is real and inverted. But there's one more scenario in the table when the object is really close. Between the pole, P, and the principal focus, F.
Exactly. This is the exception for concave mirrors. In this very close-up situation, the reflected rays don't actually meet. However, if you trace them back with your eyes, they appear to be coming from a point behind the mirror.
Behind the mirror.
Yes, this creates what we call a virtual image. You can see it, but you can't project it onto a screen. And this image is enlarged and upright. Erect.
Erect, not inverted.
Correct. This is how those makeup mirrors or shaving mirrors work. They give you a magnified upright view when your face is close to the mirror, inside the focal length.
That explains it. So that table is super helpful for understanding what kind of image you get with a concave mirror depending on where the object is. But how do we figure out exactly where the image will be and how big it will be? That's where array diagrams come into play, right?
You got it. Ray diagrams are a visual way to trace the path of light rays to find out where an image is formed by a mirror. Since every point on an object sends out light rays in all directions, we could get overwhelmed with too many lines.
Yeah, that would be messy.
So we usually just draw 2 or 3 key rays whose paths after reflection we know based on the laws of reflection and the properties of the mirror. The point where these reflected rays meet, for a real image, or appear to come from, for a virtual image, tells us where the image is located.
Okay, so what are these key rays we should draw? The special ones.
There are 4 main rules, often illustrated with diagrams like figures 9.3 to 9.6 in your text. First, a ray of light that travels parallel to the principal axis will, after reflecting off a concave mirror, pass through the principal focus, F.
Parallel in through F.
If it reflects off a convex mirror, it will appear to come from the principal focus, F, located behind the mirror.
Okay, parallel in appears from F for convex. Got it. What's the second rule?
It's kind of the reverse, a ray of light that passes through the principal focus, F, of a concave mirror.
Through F first.
Or a ray that's aimed towards the principal focus, F, of a convex mirror, will, after reflection, travel parallel to the principal axis.
Through or towards the focus. Reflects parallel. Makes sense. It's symmetrical.
Third, a ray of light that passes through the center of curvature, C, of a concave mirror, or a ray aimed at the center of curvature, C, of a convex mirror, will hit the mirror surface perpendicularly along the normal.
Right angle hit.
And therefore reflect straight back along the same path. No change in direction, just reverses.
So it hits straight on and bounces straight back. Like throwing a ball directly at a wall, it comes right back at you.
Exactly. And the fourth rule is about the pole of the mirror. A ray of light that hits the mirror at the pole, P of E, will reflect obliquely, making an equal angle on the other side of the principal axis. It's just following the basic law of reflection, angle I, angle R, at that specific point on the mirror, with the principal axis acting as the normal. Well, no, the normal is perpendicular, but the angles with the axis are equal.
Okay. Hits the pole, bounces off symmetrically across the main axis. So if I draw any 2 of these rays coming from a point on the object, say the top of the candle flame, where they meet after reflecting, or appear to meet if it's virtual, that's where the corresponding point on the image will be, like the top of the image flame.
Precisely. And by doing this for, say, the top and bottom points of the object, you can build up a complete picture of the image, its location, size, and orientation. Your resources likely have diagrams, like Figure 9.7, showing how these rays work for different object positions with concave mirrors, confirming what's in that table we talked about.
Yeah, drawing it out seems like a good way to really see how the image is formed.
Hmm.
Now, we've talked a lot about concave mirrors. What about convex mirrors? How do they form images using ray diagrams? Are they simpler?
Convex mirrors are a bit simpler in terms of the types of images they form. They are more predictable. We usually look at two main cases, shown perhaps in Figure 9.8.
Okay, what are they?
If the object is very far away, at infinity, the parallel rays reflect as if they are diverging from the principal focus, F, behind the mirror. This creates a virtual, erect, and very small, point-sized image right at the focus.
Infinity object, tiny virtual erect image at F behind.
Right. Now, if the object is at any finite distance in front of the convex mirror, say between infinity and the pole P,
Anywhere closer than infinity.
yes, the image formed will always be virtual, erect, and smaller than the object diminished, and it will always be located behind the mirror, somewhere between the pole P and the focus F.
Always virtual, erect, and diminished between P and F behind the mirror. That seems pretty consistent, like in activity 9.5 with the pencil.
Exactly. If you move a pencil towards a convex mirror, you'll see its reflection is always upright and smaller, and it gets slightly bigger as you move closer, but it never becomes as big as the actual pencil.
But why would we use them if they always make things look smaller? Doesn't seem very useful.
But think about trying to see a whole wide scene. Activity 9.6 asks about seeing a distant tree. If you look at a large object in a flat mirror, you might need a really big mirror to see all of it.
Right, you only see a part of it.
Concave mirrors can focus or magnify, but they often have a limited field of view. They only show you a small part of the scene unless the object is far away. Convex mirrors, because they make things look smaller and bend the light outwards.
They gather light from a wider angle.
Exactly. They allow you to see a much wider area reflected in a smaller mirror. Think about the side mirrors on a car. They're convex. They often say objects in mirror are closer than they appear.
Oh yeah, because they look smaller.
Right. They show you a wider view of the traffic behind you, even though the cars look smaller and further away. That wider field of view is crucial for safety. Sometimes you see them in places like the Agra Fort, apparently, offering panoramic views.
Ah, so it's about seeing more of the area,
Yeah.
even if it's smaller. That makes sense for car mirrors and security mirrors in shops. What about other uses for concave mirrors then?
Concave mirrors, because they can focus light or create parallel beams, are used in things like torches, searchlights, and vehicle headlights. If you put the bulb at the focus, the reflected rays go out parallel.
To make a strong beam.
Yes, they're also used in shaving mirrors and dentist's mirrors to give that magnified, virtual, erect image when you're close up. And because they can concentrate sunlight to a point, they're even used in solar furnaces to generate high temperatures.
So different shapes, different jobs.
Mm-hmm.
Concave for focusing, magnifying. Convex for wide view.
Mm.
Makes sense. Now, when we want to actually calculate things about these images, like how far away they are, or how big they are, we need to be really careful with our measurements and signs, right? That's where the sign convention comes in.
Exactly. To have a consistent way of doing calculations with mirrors, we use what's called the new Cartesian sign convention. Imagine drawing a standard XY graph, like in math class.
Okay, X and Y axis.
You treat the pole of the mirror as the origin, 0, 0, where the X and Y axis meet, and the principal axis is lined up with the X-axis.
Okay, P is the origin, principal axis is the X-axis. So what's positive and what's negative?
First, a key rule. We always place the object to the left of the mirror in diagrams. This means the light is always considered to be traveling from left to right towards the mirror.
Object always on the left, light comes from the left.
Second, all distances parallel to the principal axis, like object distance u and image distance v, are measured from the pole, P.
Measure from P.
Third, distances measured to the right of the pole along the positive x-axis are taken as positive. Distances measured to the left of the pole along the negative x-axis are negative.
Right, positive, left, negative, like a number line.
Exactly. Fourth, heights measured perpendicular to the principal axis and above it, like the height of an upright object or a virtual erect image, are positive along the positive y-axis.
Not positive.
And fifth, heights measured perpendicular to and below the principal axis, like the height of an inverted real image, are negative along the negative y-axis.
Down negative. Okay. Object on the left, Distances from the pole, right and up are positive, left and down are negative.
Oh.
Got it. This sounds really important for getting the math right.
It's absolutely crucial. These sign conventions allow us to use a single formula, the mirror formula, which connects the object distance u, the image distance v, and the focal length of a spherical mirror.
Okay, what's the magic formula?
The formula is 1v plus 1u equals 1f. It's equation 9.1 in the text.
1 over v plus 1 over u equals 1 over f.
That's it. This formula works for both concave and convex mirrors, and for any position of the object, as long as you plug in the values for u, v, and f with the correct signs according to the convention. Remember, for concave mirrors, f is negative, focus is usually left of p for incoming parallel light, and for convex mirrors, f is positive, focus is behind right of p. Object distance u is almost always negative since the object is on the left.
Okay, so if I know the focal length with its sign and where the object is, usually negative, I can plug them in and calculate where the image will be. And the sign of v will tell me if it's real, positive right, or virtual, negative left.
That's right. And we can also figure out how much the image is magnified compared to the object using the magnification formula. Magnification m is defined as the ratio of the height of the image, h, to the height of the object, j. So ma each I.
Image height over object height.
Magnification is also related to the image and object distances by the formula m equals my vu. That's equation 9.3. Notice that negative sign in front of the vu.
That negative sign must tell us something important. Is it about erect or inverted?
It is. A negative value for the magnification tells you that the image is real and inverted, since h would be negative if h is positive. A positive value for magnification means the image is virtual and erect, since h would be positive if h is positive.
Negative m, real, inverted. Positive m, virtual, erect. Okay.
Your textbook probably has examples showing how to use these formulas, like example 9.1 with a convex rearview mirror.
Let's see. R is plus 3.0 meters, so F is R2 equals plus 1.15 meters of convex. Object U is -5600 meters left. Plug into 1V plus 1U equals 1F.
Right, so 1v will 1f 1u equal 1 plus 1.50, 1 plus 1.00 plus 15.00. You solve for v.
Need a common denominator, like 7.5. So 5 plus 1.5, 7.5 equals 6.5, 7.5. So V equals 7.5, 6.5, which is about plus 1.15 meter, positive V.
Positive v means the image is behind the mirror, virtual, which we expect for convex, and magnification m means it's smaller, diminished. Makes sense for a car mirror.
See? It works. And example 9.2 does the same for a concave mirror, finding the image position and size. It just takes practice with plugging in the numbers carefully with the right size.
Okay, so we've covered how light bounces off curved mirrors and how to describe the images they form using formulas and signs. Now let's switch gears. What happens when light doesn't bounce off but actually passes through something transparent like water or glass? That's refraction, right?
Yeah.
Exactly. Think back to those everyday observations you mentioned at the beginning. A coin at the bottom of a glass of water seeming to be higher up than it is.
Yeah, or a pencil looking bent.
Right, or letters under a glass slab looking raised, or a lemon in water looking bigger. These things happen because the light changes direction when it moves from one transparent material, like air, to another, like water or glass. Does the light keep traveling in a perfectly straight line?
It definitely looks like it bends right at the surface where the air meets the water or glass.
That bending of light as it passes obliquely at an angle from one transparent medium to another is called refraction.
Refraction bending.
And it occurs fundamentally because the speed of light changes as it moves into a different material. Different materials, different speed.
Speed change causes the bend.
Your textbook likely has activities that demonstrate this, like activity 9.7 with the coin in the bucket, or 9.8 where a coin in a bowl seems to disappear from view and then reappear when you pour water in.
I remember doing something like that. It's like the water is playing tricks on your eyes, lifting the coin's image up.
Not exactly tricks, but the light rays coming from the coin bend when they leave the water and enter the air to reach your eye. Your brain traces those rays back in straight lines, making the coin appear to be in a shallower position than it actually is.
Okay, so our brain assumes straight lines.
There are also activities like 9.9, looking at a line through a glass slab. It looks bent at the edges and raised up if you look from above. And activity 9.10 uses pins to trace the path of light through a rectangular glass slab.
The glass slab experiment. I remember that one. The light ray goes in, bends, goes through the glass, and then bends again coming out, right?
That's correct. You have the incident ray hitting the first surface, the refracted ray traveling inside the glass, and then the emergent ray coming out the other side. Because the two surfaces of the glass slab are parallel, the bending towards the normal as light enters the denser glass is exactly undone by the bending away from the normal as it exits into the rarer air.
So the emergent ray is parallel to the original incident ray.
Exactly parallel, but it's shifted sideways a bit. We call that lateral displacement or lateral shift. The amount of shift depends on the angle, the thickness of the slab, and the material. What do you think happens if the light hits the slab perfectly straight on, along the normal?
If it hits straight on, angle of incidence is 0. Maybe it doesn't bend at all.
You got it. No bending occurs for normal incidence, I0. It just goes straight through, though it still slows down inside the glass.
Okay. Now, just like reflection, refraction follows its own set of rules, the laws of refraction.
Yes, there are two main laws.
Let's hear them.
The first law of refraction is similar to reflection. The incident ray, the light going in, the refracted ray, the light that has bent, and the normal, the perpendicular line at the surface where the light hits, all lie in the same plane.
Incident, refracted, normal, all in one plane.
The second law is the really key one for calculation, known as Snell's law. It relates the angles. It states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant value for a specific color of light and for a given pair of materials.
Sin r is constant. What is that constant?
That constant value is called the refractive index of the second medium with respect to the first medium. It's usually written as n euro, so sin r equals n euro. That's equation 9.4.
Refractive index dot n. So that's the number that tells you how much the light bends when it goes from medium 1 into medium 2.
Exactly. The refractive index is a measure of how much the speed of light changes, and therefore how much the light ray bends when it enters a medium. Light travels fastest in a vacuum. We call this speed c, about 3 times 10 to the 8 meters per second. It's only slightly slower in air, but significantly slower in things like water and glass.
So if light slows down a lot in a material, does it bend more when it enters that material from air?
Generally, yes. The refractive index of medium 2 with respect to medium 1, n euro, is actually defined in terms of speeds. It's the ratio of the speed of light in medium 1 v euro to the speed of light in medium 2 v euro. So n euro is v euro v, equation 9.5.
Speed in first medium divided by speed in second medium.
And conversely, the refractive index of medium 1 with respect to medium 2 n euro would be v euro, equation 9.6. Now, if the first medium is a vacuum, or air, which is very close, then the refractive index of the second medium is called its absolute refractive index, often just written as n or nm. It's simply the speed of light in vacuum c divided by the speed of light in that medium v. So n equals flee v, equation 9.7.
Absolute refractive index, NIAV. So a higher refractive index means the light travels slower in that material.
Precisely. We use the term optical density to describe this. A material with a higher absolute refractive index is optically denser. Light travels slower in it. A material with a lower refractive index is optically rarer. Light travels faster in it. It's important not to confuse optical density with mass density, like kerosene has a lower mass density than water, but it's optically denser, meaning light travels slower in kerosene. Table 9.3 shows some values.
Okay, so denser means slower light speed, rarer means faster. How does this relate to the bending direction?
Here's the rule. When light goes from an optically rare medium, like air, to an optically denser medium, like glass, it slows down and bends towards the normal. The angle of refraction r will be smaller than the angle of incidence I.
Rarer to denser bends towards normal.
And when light goes from an optically denser medium, like glass, to an optically rarer medium, like air, it speeds up and bends away from the normal. The angle r will be larger than the angle I.
Denser to rarer bends away from normal. That explains why the straw in water looks bent upwards at the surface. Light from the submerged part goes from water, denser, to air, rarer, and bends away from the normal to reach our eyes.
You've got it. That's exactly why.
That's a key point. So the bending depends on how the speed of light changes between the two materials, quantified by the refractive index. Now, we've talked about refraction at flat surfaces, like a glass slab or water surface. What happens if those transparent surfaces are curved? That brings us to lenses, right?
You've got it. Think about things like magnifying glasses or the lenses in eyeglasses, cameras, microscopes, telescopes. They're made of transparent materials like glass or plastic, but with curved surfaces.
Yeah, they're curved.
And they are designed specifically to bend light through refraction in very controlled ways, usually to form images.
So what exactly is a lens, technically?
A lens is a piece of transparent optical material that's bounded by two surfaces, and at least one of those surfaces must be curved, usually spherical.
Okay, transparent, two surfaces, at least one curved.
There are two main types you usually encounter: convex lenses and concave lenses. A typical convex lens, or double convex lens, is thicker in the middle and thinner at the edges. Think of a magnifying glass shape.
Convex, thicker in the middle.
A typical concave lens, double concave, is the opposite: thinner in the middle and thicker at the edges. It curves inwards on both sides.
Concave, thinner in the middle, like it's caved in.
Yeah.
Got it. How do they affect light differently?
A convex lens is also called a converging lens. Because of its shape, when parallel rays of light, like from the sun, pass through it, they are refracted inwards and converge, coming together at a point on the other side. That's figure 9.1a.
Convex converges light. Makes sense, it focuses sunlight.
A concave lens, on the other hand, is called a diverging lens. Its shape causes parallel rays of light to bend outwards, to diverge after passing through it. They look like they're spreading out from a point back on the same side of the lens that the light came from. That's figure 9.12b.
Concave diverges light, spreads it out. Converging and diverging that makes sense with their shapes. And just like mirrors, lenses have their own set of key terms, right? Like centers of curvature.
Yes. Because a lens typically has two curved surfaces, it generally has two centers of curvature, C1 and C2, which are the centers of the imaginary spheres that those surfaces are a part of.
Two C's this time.
The principal axis is the imaginary straight line that passes through both these centers of curvature, C1 and C2. The optical center, O, is the very central point of the lens, usually on the principal axis.
O for optical center.
A special property of the optical center is that a ray of light passing directly through it goes undeviated, it doesn't bend. The aperture is the effective diameter of the circular outline of the lens that allows light through. In our discussions, we usually deal with thin lenses, where the thickness is small compared to the radii of curvature, and the optical center is roughly equidistant from the two foci.
Optical center straight through, no bending. Got it. What about the focus for lenses? Is like mirrors?
Similar concept, but slightly different because light goes through. Remember, activity 9.11. Using a convex lens and sunlight, again, caution, don't look at the sun directly or through the lens.
Focusing the sun to burn paper?
Yeah. When parallel rays of sunlight pass through a convex lens, they converge to a bright spot on the other side. That spot where the parallel rays focus is the principal focus, usually denoted F2 for rays coming from the left, of the convex lens. It's a real focus because the rays actually meet there.
Okay, F2 is the main focus for a convex lens.
Now, because light can pass through a lens from either direction, a lens actually has two principal foci, usually labeled F1 and F2, located symmetrically on either side of the optical center O. The distance between the optical center O and either principal focus F1 or F2 is the focal length.
Two foci, F1 and F2, focal length as O to F1 or O to F2.
Yeah.
What about concave lenses?
For a concave lens, when parallel rays enter, they diverge. They appear to be coming from a point on the same side of the lens as the incoming parallel light. That point is the principal focus, usually F1 for rays from the left, for a concave lens. It's a virtual focus because the rays don't actually meet there. Concave lenses also have two foci, F1 and F2, symmetrically placed.
So convex lenses bring light together at a real focus, F2, on the other side. Concave lenses make light spread out, as if from a virtual focus, F1, on the same side.
Exactly. And just like with mirrors, the position of the object relative to the lens determines the kind of image formed. If you look through a convex lens at something very close, closer than F1, it can look bigger and upright. That's how a simple magnifier works.
A magnifying glass effect.
But if you look at something far away through a convex lens, the image formed might be smaller and inverted. The type of image formed by a convex lens, real or virtual, erect or inverted, magnified or diminished, depends entirely on the distance of the object from the lens, similar to how it worked with concave mirrors. Your textbook will likely have a table, table 9.4, summarizing these different cases for convex lenses based on object position: infinity, beyond 2f1, at 2f1, between f1 and 2f1, at f1, between f1 and O.
Okay, lots of possibilities for convex lenses. What about concave lenses? You said they always diverge light. Are their images simpler, like activity 9.13 with the candle?
Yes, concave lenses are much simpler in terms of images. No matter where you place an object in front of a concave lens, except maybe at infinity, it always forms a virtual, erect, and diminished image. The image is always located on the same side of the lens as the object, between the optical center O and the focus F1. Table 9.5 summarizes the two main cases: object at infinity, object anywhere else.
Always virtual, upright, and smaller with concave lenses. That's a consistent rule. Easier to remember.
It is.
And we can use ray diagrams for lenses too, I bet, to see how these images are formed, just like with mirrors.
Absolutely. Ray diagrams are very useful for visualizing lens image formation. There are three main rules, or principal rays, for drawing ray diagrams for thin lenses. You only need to draw two of them accurately to find the image.
Okay, what are the three rules for lenses? Let's reference figures 9.13, 9.14, 9.15.
First, a ray of light from the object that travels parallel to the principal axis will, after passing through a convex lens, refract through the principal focus on the other side, f2. For a concave lens, it will refract such that it appears to have come from the principal focus on the same side, f1.
Rule 1. Parallel in through f2 convex
Yeah.
or appears from f1 concave.
Second, a ray of light that passes through the first principal focus, f1, before hitting a convex lens, or a ray that's directed towards the second principal focus, f2 for a concave lens, will, after refraction, emerge parallel to the principal axis.
Rule 2. Through f1 convex or towards f2 concave, refracts parallel out. Kind of the reverse of rule 1.
Exactly. And third, the easiest one. A ray of light that passes directly through the optical center of either a convex or a concave lens will continue to travel in a straight line without any bending or deviation.
Rule 3. Through the optical center, O. Straight through, no bending. Okay, those sound similar to the mirror rules, but adapted for light passing through instead of bouncing off.
Yeah.
And diagrams like figure 9.1c and 9.17 would show these in action.
Precisely. Draw two of these rays from a point on the object, see where they intersect or appear to intersect, and that's your image point.
And we need a sign convention for lenses as well, I'm guessing, for calculation, similar to mirrors.
You're right. The sign convention for lenses is very similar to the one for mirrors, which makes it a bit easier. The key difference is that all distances are measured from the optical center of the lens.
Measure from O instead of P.
Okay. The conventions for direction are the same. Object on the left, light travels left to right, right is positive, left is negative, up is positive, down is negative.
Same directions. What about focal length?
This is important. By convention, the focal length f of a convex lens converging is considered positive. The focal length of a concave lens diverging is negative.
Convex F positive, concave F negative.
Got it.
Object distance U is usually negative because the object is typically placed on the left. Image distance V is positive for real images that form on the right side of the lens, where light actually goes after refraction, and negative for virtual images that usually form on the left side, same side as object. Heights, H for object, H for image, follow the up positive, down negative rule as before.
Consistent rules make it easier to keep track of everything, and that leads us to the lens formula, I assume. Is it the same as the mirror formula?
Almost, but with one crucial difference. The lens formula relates the object distance U, the image distance V, and the focal length F for thin spherical lenses. 1V, 1U equals 1F. Notice the minus sign here between 1V and 1F.
1V minus 1U equals 1F. Mirror was plus, lens is minus. Okay, gotta remember that. Equation 9.8. Exactly. This formula, along with the magnification formula for lenses, allows us to calculate the position, size, and nature of images formed by lenses as long as we use the sign conventions consistently.
And the magnification formula, is it image view like mirrors?
Nope, another small difference. For lenses, the magnification M is still the ratio of image height to object height, mu/h equation 9.9, but it's also given by M plus VU. No negative sign in the VU part for lenses. Equation 9.9.
Oh, M view for lenses. Positive view. How does the sign of M tell us about the image then?
It works the same way regarding interpretation. A positive magnification, M0, means the image is virtual and erect. A negative magnification, M0, means the image is real and inverted.
Positive M is virtual, erect. Negative M real, inverted. Same interpretation, different formula, view versus view. Okay. And there are examples for lenses too, like 9.3.
Yes, example 9.3 involves a concave lens. The give image is 15 centimeters, negative for concave, and a virtual image formed at V equals negative for virtual is same side. You use 1V, 1U equals 1F to find us.
So Nevis 1U, 1F, 1V equals 115, 115, 110, common denominator 30, and it's 2 plus 3, 30 equals 130. So Nevis 1U equals 130, which means U equals 130 centimeters. Object is 30 centimeters to the left.
Perfect. And magnification M equals view U equals 1 Nevis 10. That is 30 equals plus 13.
Positive M means virtual, erect. 13 means diminished. one-third the size, matches what we expect for concave lenses.
Exactly. Example 9.4 does a similar calculation for a convex lens forming a real image. It's all about applying the formulas with the correct signs.
So just like with mirrors, if I know the lens's focal length with its sign and where the object is u, I can figure out where the image will be, v, and how big it will be using mView.
Precisely. And finally, let's talk quickly about the power of a lens. We know that some lenses bend light more strongly than others, right? A lens with a short focal length bends light very sharply.
Yeah, a stronger magnifier has a shorter focal length.
Exactly. The power of a lens, P, is a measure of this degree of convergence or divergence. It's defined simply as the reciprocal of its focal length, but importantly, the focal length must be expressed in meters. So P is 1F, where F is in meters. That's equation 9.11.
Power P equals 1 divided by focal length in meters. Okay, what's the unit?
The SI unit of power is the dioptry, symbolized by D. So 1 dioptry is the power of a lens whose focal length is 1 meter. 1D equals 1 more.
Dioptries, that's what they use for prescriptions for glasses. I've seen that D symbol.
Exactly. Since a convex lens has a positive focal length, its power is positive. A concave lens has a negative focal length, so its power is negative.
So positive power means converging lens, negative power means diverging lens.
Right. If your eye doctor gives you a prescription of plus 2.0 D, that means you need a convex lens with a focal length F equals 1T equals 1 plus 2.0 plus 0.50 meters or plus 50 centimeters. If the prescription is -2.5 D, you need a concave lens with f1 diameter 2.5 equals 0.40 meters or -40 centimeters.
Makes sense. Easy way to specify lens strength. What if you put lenses together?
Another neat thing is that if you have several thin lenses placed in close contact, their total effective power is simply the algebraic sum of their individual powers. P total is P1 plus P2 plus P3 plus the.
Powers just add up. That seems convenient.
It's very convenient, especially for opticians when testing eyes. They can combine lenses easily to find the right correction. It's also why complex optical instruments like cameras, microscopes, and telescopes use combinations of lenses. Putting multiple lenses together allows for greater magnification, control over aberrations, image imperfections, and overall better image quality.
So stacking lenses gives more options. That's pretty neat.
It is. So in our deep dive today, we've covered quite a lot of ground, haven't we?
We really have. We started with the basic idea of light traveling in straight lines, then looked at how it reflects according to specific laws, how that works for plane mirrors, and then curved spherical mirrors, concave and convex.
Right. We talked about image formation by mirrors, real, virtual, magnified, diminished, inverted, erect, and how to use ray diagrams and the mirror formula with sign conventions to figure it all out.
Then we switched to refraction, the bending of light when it goes from one medium to another because its speed changes. We looked at Snell's law and the refractive index.
Yeah, and optical tensity. Then we applied refraction to curved surfaces lenses, convex converging lenses, and concave diverging lenses.
Yeah, and how they form images, again, using ray diagrams, the lens formula with that minus sign, magnification, and the sign conventions. And finally, the power of a lens in dioptries.
It's incredible how these fundamental ideas about reflection and refraction underpin so much of our world, from how we simply see our own reflection to the complex technology in eyeglasses, cameras, and telescopes that allows us to see the incredibly small or explore the distant stars.
It really makes you think. We've focused on mirrors and basic lenses, but these principles must be at play in so many other things, like how exactly does a rainbow form using refraction and reflection inside raindrops? Or how do optical fibers transmit information using reflection?
Those are fantastic questions. It shows how these core concepts branch out into countless fascinating phenomena and technologies. The bending and bouncing of light really shapes our entire visual experience and much of our modern tech.
Definitely food for thought. What other amazing phenomena might be explained by these basic principles of reflection and refraction? It makes you want to keep looking and figuring things out.
That's the spirit. The world of optics is vast and full of wonders, from the intricate workings of the human eye itself to things like holography or the latest advances in microscopy. Perhaps we can explore some of those in future depth dives. Until then, keep looking closely at the world around you and noticing the amazing ways light shapes our perception of it.